Okay, this is Math 116, Section 2.3, and this is the application problems that go along with quadratics. We have some of those same definitions that we saw back in 1.6. Profit equals revenue minus cost. Remember, revenue is how much we take in, cost is how much we spent to make it. So when these two equal zero, then the profit would be zero, which we also have down here, which is our equilibrium point. To find equilibrium, we can do revenue equals cost or P equals zero. Profit and revenue are pretty straightforward. Cost, I'll just remind you that we have variable cost and fixed cost. So fixed cost was things like rent, where we have to pay that money whether we make or sell any of these things or not. And then variable cost is how much it costs to make each individual unit. So things like labor or materials. And then lastly, market equilibrium is when the quantity of commodity demanded is the same as the quantity supplied. So there's going to be two basic styles of math in this section. One is where we're solving quadratics, like what we did in 2.1, and that's where we're looking for zeros. We're looking for where x equals 0. And then the other is going to be the math that we saw in 2.2, which involved the vertex, and that's going to be maximum and minimum problems. So this first one, company has a total cost of that, total revenue given by that, find the break-even points. So in this case, remember we have cost equals revenue, so we're going to set these two equations equal to one another. And then since it's quadratic, I want to get it equal to 0 to be able to solve it. So I'm going to add the 0.8x squared to both sides. And then take this one away since it's positive. And then I'll write it in descending order just kind of for convenience. So 0.2 and 0.8 would make 1x squared. 15 minus 265 would be minus 250x. And then 10,000 equals 0. So this one does actually factor, but it's not the easiest thing to see how to factor. So probably the better bet is just to throw it in the quadratic formula. And that will look like negative b, so negative of negative 250 plus or minus negative 250. Careful to quantity square that. Sometimes people will put the parentheses and then this comes up negative. Minus 4, a is 1, and then c is that 10,000. All over 2. So then next I threw all this in the calculator and took the square root, and that got me to x equals 250 plus or minus 150 over 2. So that's going to be two distinct answers now, where we would break even. And so the first one is 250 plus 150 would be 400 over 2, so that would be 200. And the second one is 250 minus 150, so that would be 100 over 2. So we break even when we make 50 or 200. And probably somewhere in between there we get to make money, is the idea. Okay, number 2 goes find the maximum revenue for the revenue function that round to the nearest cent. So when we see maximums or minimums, then with parabolas, remember that's where the vertex is. So if it's opening down, we'd have a maximum. If it's opening up, we have a minimum. So we're just going to do the x equals negative b over 2a with this to get the x coordinate. And b is the 365. And a is the negative, oops, that should have a negative in front, negative 0.9. And then if you throw all that in a calculator, that comes out to 202.7 with a bar on it. The deal is that we're not looking for the number of units that maximize the revenue, we're looking for the actual maximum revenue, and so R is the output, so it's like the Y. So we have to plug the X back in now and then get the Y that would go with it. So let me write out what I'm going to put in the calculator. Okay, so here I set up the equation I'm going to put in the calculator. I should have written R of 202.7 with a bar right here. But so this is what I'm going to plug in. I put this little chunk of math in the calculator, and here this is with all the decimals. And it's important to keep all those decimal places because otherwise you'll be off in the cents part of the problem because you're rounding to the nearest cent. On a test, I would totally mark it right, but the computer may be programmed to take exactly that one answer that it gets if you keep all the decimals. So to do that easily, so you don't have to type all this mess, I just go 365 and then times second function for me, and then answer is right here. And what that does is it copies the answer from the your last answer that you just calculated, which was this number, and pastes it here. And then you don't have to type all that mess out. So somewhere down in here you will have a button that says answer, and it's different on different calculators, but you're going to want to find that. And then we're going to go minus 0.9 times, and then again second answer, and it just copies that in, and then squared. And then there's our answer. Okay, number 3. If in a monopoly market the demand for a product is given by P equals 165 minus 0.4x, and the revenue function is R times P of x. So remember, they just gave us P right here, and now they're saying here's how we're going to get to the revenue function, and the x is the number of units sold. What price will maximize revenue? So we have R equals P, which is the 165 minus 0.4x times x. And then multiplying that through, I'm going to get 165x, just plain x, minus 0.40x squared. So this is our revenue function. And it's quadratic and negatives, that means it's opening down. So the vertex again is going to be where revenue is maximized. So if we do our x equals negative b over 2a, that's going to go negative 165 over 2 times negative 0.4. And then I threw that in a calculator and got 206.25. So this is the number of units that would maximize the revenue, but the question is asking what price will maximize the revenue. So we actually have to put this back into the price equation, not the revenue equation, because it's not saying what's the maximum revenue, it's saying at what price does it happen. And that's where you just have to kind of be careful as we're reading these. So P equals 165 minus 0.40 times that. And again, we want to keep those decimal places to make sure that we're right in the rounding. And that comes out to 82.50 when I did it. Okay, for number 4, we're supposed to first graph the profit function, this. And so this is what the graph would look like. I'm not expecting you to graph that by hand. That's kind of miserable. Go to desmos.com if you don't, or you could use a graphing calculator. This is actually easier because it's much easier to zoom out rather than mess around with setting the window. And then you can, I think it's a multiple choice question, so you can just graph this in Desmos and then compare it, and then that will help you check kind of the features of the graph. B, find the vertex of the graph. That's something I would ask you to do by hand because that's just our x equals negative b over 2a. So they messed with the order a little bit, so we gotta be careful. There's B, so negative 70 over 2 times, and then there's A. Oops. And then I just threw that in a calculator and got 170, can't write, 175. And then we're finding the vertex, so this is only the x-coordinate. So now I have to go back and put this 175 into the calculator. And again, I just plugged 175 here and here. And when I did that, I got y is, actually I guess that's p, is 4,125. Okay, and then part C of the question is the average rate of change for this function from x equals a less than 175 to x equals 175, positive or negative? Okay, so that was a lot of words. So we'll come back here and we'll look at our graph. Here's 175, somewhere right around there at the vertex. So where these are less than is the slope positive or negative, because remember, average rate of change is like our slope. So here we would say it's positive. For D is the average rate of change of this function when the a's are greater than, so we're on this side, positive or negative, so that would be negative. And then, does the average rate of change of the profit get closer or farther from 0 when a is closer to 175? So when we're right at 175, if we drew a line tangent to the graph, it would be flat, and m would equal 0. So the closer that we get to the vertex, the closer the slope gets to 0. So we'd say closer to 0. Okay, I think number 5 is like the longest math question ever. So suppose a company has a fixed cost of this and a variable cost per unit of this, where x is the number, the total number of units produced. So we got fixed cost and then we have variable cost, but now our variable cost is variable, and so that's going to lead to a quadratic equation out of this. Suppose further the selling price of the product is given by this. Find the break-even points. So that means we need to get a cost function and a revenue function together. So the cost is, remember, it goes variable cost times x times the number of units plus fixed cost. So this is going to look like, there is our fixed cost, there's our variable cost. So our variable cost is going to be x times 2/5 x plus 444. And then that's going to be plus 4,800. I'm sorry, 48,000. And then distributing that through, I get a cost function of 2/5 x squared 444x plus the 48,000. So then I'm going to do a revenue function. So its sell price is this. Remember, price times units gets us revenue. So revenue is going to be x times this. And so that's going to be 1976x minus 3/5 x squared. So now I have a cost function and a revenue function, and I'll set them equal, and then, because remember, we're looking for break-even point, so that's where cost equals revenue. So we'll set them equal and then solve that. Okay, so I rewrote our cost function equals our revenue function on a new piece of paper, and now I'm going to bring all this over, so I'm just subtracting this and I'm adding this. And then that's going to be x squared minus 1532x plus 4800 equals 0. So, again, it does factor, but that's some pretty terrible factoring, so I would probably just throw it in the quadratic equation. And so I'll have negative of negative 1532. So 1532 plus or minus negative 1532 squared minus 4 times a times c all over 2a. So then I threw all this in the quadratic and I took the root, and that got me x equals 1532 plus or minus 1468 over 2. And then if you do the 15 plus the 14 divided by 2, that ends up coming out to, I think it was 1500. And if we do 1532 minus that divided by 2, that one comes out to 32. Okay, part B is find the maximum revenue. So remember back here we found the revenue function, so I'll just copy that to here. And r of x equals negative 3/5 x squared plus 1876x. And so then to find the maximum, we're going to do the vertex, or find the vertex. So x equals negative 1976 over 2, and then negative 3/5 is the same thing as negative 0.6. So I just put it in the calculator that way. And that got me, 1646, and then 6 with a bar. And this is asking for the maximum revenue, again, not the units that maximize the revenue, so we have to do that next step, which is finding R of 1646. And again, I would have this value on the calculator, and then using the second function in the answer, just drop it right in here, and you should get this big number. If you don't know how to use that answer key, I showed it earlier in this video, or you could definitely ask me in class. It will make this much, much easier if you know where that button is on your calculator. Okay, part C, form the profit function from the revenue and the cost functions. So we actually just about did that back here, but I brought this over and made it positive, just to get this leading term positive. But this was cost and this was revenue, so we need to go revenue minus cost to get the profit function. So it's going to be this exact same thing, except the signs are all backwards. It's just if we had solved the other direction. Okay, and then given that profit function, find the maximum profit. So that's going to be x equals, again, we're doing vertex, anytime we see max or min. And that comes out to 766 units. And then we're not trying to find the units, we're trying to find the profit. So then I just take this and back solve it in here. So when I found P of 766, I got 538,756. And then the last question is, what price will maximize the profit? So for that, we have to go way back to the beginning. And remember, back here was our price equation, back in the early directions of the problem long, long ago. And so that was P equals 1976 minus 3/5 X. And then this was the number of units that maximized the profit, so this would be the price it happens at. So we're just going to put the 766 in right here. And when I did that, I got $1,516.40. Okay, number 6 goes to supply and demand for product are given by these two equations. That's our supply, that's our demand. Find the equilibrium points. Remember, that's where supply equals demand. So what we have to do is basically just solve the system of equations. But this time, instead of being linear, it's going to turn out nonlinear, so we're going to have to use quadratic formula again to work that out. So I'm going to do this by substitution because this multiplication right here is going to mess things up. So I'm going to bring this q over to this side and the 70 over to this side. So this equation I'm going to think of as 2p minus 70 equals q. And now that I have this in terms of q, I can plug it in here and here, and then that's going to give me an equation all in terms of p that I can solve. So let me get that written out. Okay, so here it is with the 2p minus 70 substituted in for this q and then for that q. And now I'm going to go ahead and clear all these parentheses. So 2p squared minus 70p, 200, and then just run the 20 through. So that'll be 40p minus 1400. And then it's quadratic, so I'm going to bring everything over to one side and solve. So actually, before I do that, maybe I'll 2p squared minus 70p equals 40p, and then 200 minus that would be minus 1200. So I'm going to collect terms first. So now I'm going to subtract this one over and add this one over. So that will be 2p squared minus 110p, and it'll be a plus 1200 when I bring it over. So now I have a quadratic equal to 0, so that means we can use the quadratic formula. And again, this one factors, which I did show at this time in the notes, but it's fairly terrible, so I again would just encourage you to throw it in the quadratic. And if we're putting in the quadratic, we can do this one little sneaky thing that I did do in the notes, which is everything here is divisible by 2, so I'm just going to reduce a 2 out of everything, just to make the numbers a little bit smaller in the quadratic is all. So, and you do not have to do this step, you can just put them in just like they are and it'll be fine. But just to stay consistent with the notes, here's what I did. So I just reduced out a 2. And now plugging all that in, plus or minus negative 55 squared, and 4 times A times C all over 2A. And then I plugged all that in and got P equals 55. And doing this up, I got 625, and then the square root made 25 over 2. So there's two values for P. So 55 plus 25 would be 70, 80 over 2, so that one would be 40. And then if we do minus, that'll come out to 30 over 2, so that one would be 15. Okay, I ran out of room on that last piece of paper. So where we were was we had found two possible price points that would result in Markov equilibrium. So a price of 40 or a price of 10. But we have to see if the quantity makes any sense with that. So we'll take our price and put it back into our equation that we solved earlier. And this is the one that I solved to do the substitution. So in this case, the quantity I get is 10. So that makes sense. The equilibrium point will be 10 are supplied for a price of 40. Here, if I put this back in, I get Q equals 2 times 10 minus 70, or Q equals negative 40. So that does not make sense as a quantity. So the price of 40, quantity 10 is the only reasonable answer that we get for this.